So good morning, everyone. So my name is Dany, and I am now a professor at Institut des Sciences de la Mer de Rimouski in Eastern Canada, in Québec province. I've been there for 6 years, and I'm going to talk about some work I've been doing. I've been starting during my postdoc at the Nansen Center in 2009. And it's going to talk about sea ice fracture in the marginalized zone. And my goal in this talk, as part of this sea ice program, is to bring some ideas towards what we know and what we should do in the future to better understand the question. So I'm an oceanographer by training, and that's going to set the focus of the research of the presentation here towards understanding what's going on in the marginalized zone as a whole. So I've been from the start inspired by the pointers here. Okay, inspired by looking at many satellite images of the marginalized zone. I wasn't that familiar with that zone when I started. So when I fell on a lot of images like these, where you have and of course that are familiar to those who have been studied this area. Where you have the open ocean and the inner pack ice, which looks like brittle plastic material with long ice cracks, really big ice floes, tens or even hundreds of kilometers wide, and in between a transition zone where from that scale it looks like a slurry or slush or a really viscous material. So then the question I was asked at the time is to work out how sea ice models can resolve or simulate the dynamics of that area. And pretty rapidly we have to realize, and it's been known, I mean, that waves have a huge impact on that dynamics. And here are a couple of reasons why. So of course waves break up sea ice flows in the order of 1 to 100, a couple of hundreds of meters that are unresolved by satellites. That's why we can't see the individual flows usually on satellites. And on that image, there appears to be a clear transition between small flows and larger flows. So broken up flows and unbroken flows by waves. Another aspect is that absorbed wave momentum. We know that waves are attenuated, and we'll talk to that later, but absorbed wave momentum can also impose an additional force on the ice that is not taken into account now. And eventually, if waves are propagating in that and attenuate and lose energy and momentum, so that dissipated energy must go somewhere. So there's a question here to be asked, and it goes into the breakup, but it may actually go elsewhere in the ocean, producing some mixing, which is important in the energy and heat fluxes in that area as well. And the fact that waves are propagating here, they agitate flow, they move flows around, can also modulate heat fluxes in this area, and also the rheology, the dynamics. So with more recent sentinel image at higher resolution and more frequency in the marginalized zone, then we can see those. This is an example taken on the Ocean Data Lab website. It's a sentinel image where we actually see the ice edge, some bands, and we actually see waves propagating. I don't know if you can, but I'll just zoom in on that area here. So this is here that you have a scale. It's approximately that wide. It's 2 kilometers. So approximately 300-meter waves are propagating into sea ice, probably now something like 30-40 kilometers from the ice edge. And it's basically, you see this large ice flow here that's start disintegrating really. So it was like the edge, we can still see it, but soon I assume that it may become like this homogeneous slide of ice here. So flow breakup occurs right there. Unfortunately, we cannot, with satellites, see what's going on like in 10 minutes more, or at how this process is actually evolving in time. So I will present also later some field work that aims at understanding and observing what's going on at the proper scale here. So how do we, with the current state of sea ice models, they are not able just to take into account these the size of flows and waves and all this stuff. So there is a need to integrate what exists in wave models, and Elise has introduced that yesterday, and sea ice models. So they are rather both single incomplete to describe the phenomenon that we're interested in. So at that time we came up with a model integration strategy, and like to see what's the first step to do, and then to where are we heading. So eventually what we would like is to have all these models coupled, because they matter. The atmosphere matters to the ocean and sea ice, and in the boundary layer it's really an active zone where everything matters, a lot matters, especially in marginalized zone where all these things interact pretty strongly. So we designed that strategy to eventually that all these models will be coupled, but this module, or this like the interactions, the strong interactions between sea ice and waves that we wanted to understand and begin to study. So and what do we couple? How these models communicate? So wave models, we'll see that they solve for the wave energy density spectrum. So I call that E of the wave number. And then the sea ice model needs to know that, or needs to be affected by this at some point, in order to affect the flow size. And flow size should be a state property of the ice itself. And we'll define this quantity a bit later, but that's the flow size and thickness distribution. And the wave model needs as well the information about flow size, because presumably the wave propagation will depend on the sea ice property, both flow size and thickness, and maybe other parameters, because sea ice is still, I don't believe sea ice can be reduced to this, but it's a step forward. So sea ice models. I'm just presenting like this one equation here that deals with the momentum balance of sea ice. That is the form that is currently adopted, except for this term here. So this acceleration, Coriolis force, the ocean tilt, the wind, the ocean current. This is a new term taking into account the fact that sea ice can interact with the seabed. That's not relevant for our talk here. This is the wave additive force, so waves pushing on it. It strictly depends on waves, and the rheology term. So the rheology is the constitutive relation between the stress and the strain rate, and this is one formulation where we see that the pressure, or the compressive strength, is a function of thickness and concentration, and everything else, like the viscosities, the nonlinear viscosities, that will decide whenever the ice flows or not with that yield curve, depend on as well only ice thickness and concentration. So there's no flow size available there for modifying for example, the shear strength. So the image that I showed earlier suggests that if you have even high concentration ice, but that's all broken up, then the shear resistance must be in some way reduced. So that will affect the rheology in the end. So what we have so concentration and thickness are evolved in the sea ice model as through this equation, which is the ice thickness distribution function. So we describe the ice as having a distribution, and then thermodynamic flux depend on the thickness. Here, of course, it's advected, and you have mechanical redistribution of these thicknesses in different categories. And then we extract the mean of that, and we use that for the rheology. So what has been proposed as a step forward to couple these wave and sea ice processes is to generalize this equation laid out by Thorndike in 75 to a more general equation that will include a flow size and thickness distribution. So R is the flow size variable. That includes processes here, like the thermodynamic ice growth and melt is included in that thermodynamic term operator that acts on the distribution. You have advection, you have mechanical redistribution, and you have the wave breakup eventually. So we'll discuss that a little bit later. So what this term looks like. So it's basically a breakup probability. So you have flows of one flow size that when breakup occurs, it will be broken up in smaller flows. So you lose flows of that size and you gain whatever larger flows are broken up into that actual size. So the integral of that operator is 0. It doesn't change the overall area, but redistribute flow sizes. So the other let's say term in the momentum balance is the wave radiative force, and here's just like the formulation of that radiative stress, which translates into a force when per unit meter when you take the divergence of this. And the stress will depend on how the wave attenuation, on how the waves attenuate is absorbed by the ice. So if we assume that all the momentum is absorbed by the ice, then it translates into a force on the ice, and in this. So I will briefly talk at the end about that term, which is not related to fracture per se, but it's important in the context. So this was sea ice models. Then in the wave model, we can reduce the equation to this. So advection of the so sorry, here I use F, but it's the previous E. So the energy frequency, wave energy density spectrum, and a couple of source terms, including the ice terms. And this ice can be written like this, so it can be scattered and it can be dissipated. And we, of course, there are still a lot of research and questions related to how how can we parameterize and model these attenuation or scattering coefficient. But generally, it can take this form. So redistributing energy in the direction and dissipating the energy as well. So for example, Bennett and Squire and many others have computed this scattering coefficient and used that as a way to parameterize attenuation under the assumption that all the scattered energy is going in the backward direction and is removed from the forward direction. So it attenuates energy in the way forward. And the way and it depends on the size of the flow compared to the wavelength. So in a way, if we want to compute a dimensional coefficient, we need to scale that up with some sort of average flow size as well. So just to point out that there is a relationship between, potential relationship between wave attenuation or propagation and the flow size, so the flow breakup, which depends on waves as well. So there's a really strong coupling in waves and sea ice. That's my point here. And of course, either if it's scattering or dissipation, there is a strong dependence upon period and potentially ice thickness as well. Both dissipation, and scattering. So those are our models. They are still to be validated compared to data, and we'll come to that later. But they can be used now, and they have been validated with current data sets available. And they are representing how energy, or to what extent waves propagate in the MIZ. So they are, and we will be using them into a simple model later to say something about the marginalized zone. So yeah, the first question we can ask is if we try to couple these things together, flow breakup and wave attenuation. How are they working up? So to answer this question, we built a simple one-dimensional wave advection attenuation model with a flexural flow breakup parameterization. That is, I mean, this flow breakup is highly based on empirical evidence on flexural strength, and you'll see other assumptions as well. So the conceptual model in 1D, you have waves propagating into marginalized zone. When you look at any kind of data or model output, there is an increasing thickness from the ice edge inward. And so we want to have a numerical discretization where we advect waves, and here you have waves, you have waves propagating and breaking up ice until a certain point where waves can still propagate, but they won't break up ice due to not enough energy. And that will produce smaller flows as we go in. And eventually, when the breakup stops, then that's where we define the MIZ extent. So we'll look at that extension here. So how do we parameterize the flow breakup? Yeah, there has been many attempts. I show you one here, where we can compute a significant strain. That's a contribution from all waves in the wave spectrum, and that depends on the curvature of the waves and the thickness. And we compare that in some way with a critical strain that has been measured or evaluated many times. Here we pick that value. It can be tuned as well, and of course it strongly depends upon the properties of the ice. But over the scale that we use, it's a tunable parameter that maybe we can change and do sensitivity analyses on. So in the context of random waves, then what we define is a probability of exceeding that critical strain, and compare that. I mean, say that there is a breakup whenever the significant strain is over that significant critical strain modulo a critical probability of exceeding that strain. And then what happens? This is really naive assumption, but when the ice breaks, it will break approximately at the scale of the wave. So we chose half a wavelength, pretty naively, and this is up to validate, and we'll come to that. And if it doesn't break, then we don't do anything with the flow size. And then when it breaks, of course, there's not one single size. We looked at the observation, and here is aggregated observations from many aerial pictures in the Arctic showing that there is a flow size distribution. Yeah, we can argue that it is a power law, or it's different shapes, but anyway, we can use as a first order approximation like a power law, and then work out this average flow size. And we'll see that anyway for the wave breakup, if the domain is if the range is small, then it doesn't do a lot of difference if we play with that exact distribution here.
So that flow size distribution is independent, is without regard to thickness.
Not now, not in this, but I'll come to that later. Of course it is, yeah. So this is for the first results we obtain, and we have the significant wave height, the wave period that we send into our transect. So we use the output of the topaz model. This is the thickness of the model, up to 0 to 4 meter here. This is the ice concentration. There's a lack of sea ice in the summer, so underestimation. And then you have the broken up ice in colored, okay? And black is unbroken. So those two results are if we take the original thickness, or if we double it, and the double one is more in adequation with observations that have been taken some years earlier than that in Fram Strait. This is representative of Fram Strait here. So this kind of result to us represent more what the model would do, but we don't see, I mean, it's hard to validate that. That's the next step. But what we can learn from that is there's an abrupt termination of the breakup. So waves go in and then it stops. And the marginalized zone is highly driven by the incident wave energy and highly sensitive to ice thickness as well. So what do we do from now? Is it representative of reality or what? So we did some sensitivity analysis, but that's not enough. And of course, it's a 1D model. So we wanted to check what is there data there. And of course, satellites, there's no assessments of flow size from satellites, and there's no systematic work that has been done on that area to extract the marginalized zone width. So we looked at the ice charts. So for those who are not familiar, ice charts are produced by National Ice Services. Here I will show those from the Denmark's Meteorologisk Institute, who use the egg code as information on the flow size. So you have the total concentration in tenths here, and there is information about the form of ice, which is the dominant flow size. And it's really crude in categories, but if we choose flow size less than 4 and less, that represents flow size of 500 meter and less. And then the next category is up to 2 kilometers, which is way larger than our prediction in the model. So if we use like a full year of these ice charts, so the egg code is associated with 1 polygon areas. And it turns out that if you select like the polygons with the smaller flows, like our MIZ flows, they always are, of course, on the ice edge. There's no like polygons in the inner ice. It's a good sign. And then we take all the polygons and then we try to merge them. Of course, here there aren't. But we take that into account in our, let's say, the whole marginalized zone extent that we want. Like this is the convoluted polygon that's representing the marginalized zone in the ice chart. So what do we want to do with that? It's we want to compare, like to compute an effective width of that area. So we use the Euclidean distance of the polygon, and we compute the average along the skeleton. So that's a method to compute the size of objects that are really irregular, like the convolution in your brain and stuff. So it gives a number that's representative of the whole area. But we can also separate these in some stripes and compare with waves that are impacting at that area. So it's not, it doesn't validate for events because you have 1 stripe per week and you have a really high, really large region, and it's, of course, waves are traveling in many directions, the ice advex and stuff. So it's not pure validation of wave ice events. But what came out of that is if we have a criteria that is based on flow size purely, not concentration, we have, so this is summer, this is winter, this is the January here. So we have a larger marginalized zone during winter, during a time where the waves are larger. And those are the model results here in terms of width. And here, this is the overall width, and we have here the same, let's say, seasonal pattern, overall sub-regions along that transect. So up in Fram Strait here. And if you compare that with the concentration-based marginalized zone, which is like loosening the ice edge without breaking up the flows, then you have a higher signal in summer. So this is inverted. Winter is here. And so here we have an adequation between the seasonal pattern of the model and the observation. So similar results were obtained also by Vaughan and Squire using yet another model similar based on flexural breakup also. So we have during winter larger marginalized zone extent also in 1D here. Okay, so but we can go further than this in trying to say what if the processes we try to parameterize are representative of reality. So And if we look around, there's a profound lack of observations at the proper scale to say something more about these processes. So which mechanisms are responsible for wave attenuation? Where does the scattered dissipated energy of the waves go? How does the flow size distribution evolve as a function of thickness, for example? We don't have that in the observations that clearly. How does this process depend on other ice properties, if it's brash or multi-year ice or whatever? And when do sea ice breakup happens? Like how at the scale of an event? So now I'm going to present field work that we've been carried on, motivated by this, and also by the fact that so the university I'm working in is here on the south shore of the St. Lawrence Estuary and Gulf. So this is the Gaspésie Peninsula. It's here. Quebec is not even here yet. So you have the St. Lawrence. So this is all salt water, seawater. Okay, it's an estuary. It's the 34. You have the Saguenay Fjord. It's an estuary because it's highly driven by tides there. And of course, it's seasonally ice covered. This is in January, like ice kicks in late December, early January in the estuary. And so we are, the institution is here, and what I'm going to show you is field work that we've been carried on near Rimouski. So this is a 350 meter high hill in the Bic National Park. And we're looking here west, so upstream the estuary. And in this area during winter there is a sensible heat polynya driven by heat tidal heat brought by tidal mixing. So it is perfect for having a stretch of open water generating waves. We have a 80 kilometer fetch producing some significant waves there. And here there is a bay which it's oriented towards the west, which is impacted by the wave and also collects the ice that flows downstream. So it can freeze up, break up, and then freeze up again, like multiple times during one thing. No, yeah, no, but it's straight. No, this is roughly straight, but it's a GoPro or panoramic picture. But this is a park, so there are islands, and it's here it's straighter. But
sea ice. Is it pretty stable?
This is sea ice. This is brash. I'll show you. Yeah, but typically when this becomes land fast, it's 40 centimeter. Okay. Let's say 25, 40.
Or it breaks up?
No, it breaks up. But it can be stable for weeks, and then you have it depends on. I'll show you some. Yeah, it's highly variable. It's really hard to say one number here. Baie du Haha, yes. I can tell you the story after that. It will be long. So here are the mean conditions. So you have we have an instrument deployed there that measured waves for 4 years, and because of the island, there's an island here, so it blocks waves that could come here. It comes either from the northeast or west. So and of course this is the longer fetch, but less fit for carrying experiments here. So the dominant waves we're looking at are from the west, typically 4.5 to 6 second waves, peak waves, and 1 meter in significant height. That's the climate of the area. So we started by just deploying a camera here, and I will show you predominantly results from that camera doing time lapse. And we have instruments underwater as well, and acoustic Doppler current profiler, which records waves, and has also surface track mode, which can help retrieve ice thickness. And we have pressure gauges that also measure waves. It's a shallow environment, so here it's around 5 meters to 18 meters, all these instruments. So that allows to measure waves in two ways. So with the non-hydrostatic wave pressure and on top of the ice with wave buoys. So we have used drones and as well devices to measure turbulence under the ice. That will help us, answer many questions, we hope so. So I'm going to show you results from the camera. So this is the one typical image of the camera, and then we rectify it in order to map it on a horizontal plane. And I'm going to show you results from 3 events that occurred over the last 3 years. Unfortunately, for those 2 events, we didn't have the AWAC deployed, so we have waves measurements only for the 3rd one. Yeah. Is it the one? Yes. Okay. So this is a geo-rectified image with contrast enhanced that will show. You must see the waves propagating into that ice, and here it's land fast, and it starts to break up. And because of the flow, immediately you sea ice drift away. I can redo that. So this is land fast. Here you have the shear zone, and wave breaks up the ice.
So you're saying waves are breaking up the ice?
Yep.
Are we supposed to see that? Or?
I mean, we see waves and we see break up, and then.
You can't see the waves.
Sorry?
You can't see the waves.
You haven't seen the waves. Okay.
Where are the waves?
Should stop. Those are waves. Okay, approximately like, this is a wavelength. Oscillating here. It's hard to see them.
A lot more exciting stuff in there.
Sorry?
There's a lot that was more exciting.
Yes. More exciting?
More movement.
Yeah.
There's also some flow happening up to the upper right. There's also some flow.
Yeah, of course. This is tidally driven, so like.
So how can you tell that it's wave driven and not flow driven breakup?
Yeah, great. Any answer? So if you have and on the second, let's show you. So if you know like how the force of the current act on the ice, then it's a cumulative stress. If it's land fast, then at some point you'll have one force, that is the force of the current, friction. But eventually it will also accumulate, and if you have the friction here that pushes on the ice, so you have a tensile stress or force that will accumulate and eventually reach that limit, but a certain distance from the ice edge. So now what we see is waves is breakup happening in like sequentially, like in a sequence from the ice edge inward. While if it was a current, like breaking the ice under it here, you would have a breakup happening somewhere further before it happens here. Okay, because you have the cumulative stress under the ice.
What's the ice thickness roughly?
Here we haven't measured yet, but it's typically 25 to 40 centimeter here. But you have here it can be rubbled and a bit ridged, but it's not like 3 meters. Okay, and then we have a close-up of that event.
What's the time scale of that?
Every image is 2 seconds.
What's the
2 minutes.
scale-
2
what's
minutes.
the scale of what you're showing there on
Yeah.
the right?
Let me show you then. Okay, so this is the movie. Here we have like a sequence of what's happening in that event here. So you see the tip of the trees here. Those are typically 20 centimeter pixels that we see. This is 15 meter roughly. Okay. So what I'm going to do is to follow one specific flow that has been freshly broken up here, and so it's breaking up in the other direction, and then breaking up again, flowing with the current, and then breaking up again.
It's like a breaking front moving through this.
Exactly, exactly.
That move, how would that speed ahead of the group speed?
Okay, let's. It's
Is that the
4 slides later.
I'm sorry.
Yeah.
Really score.
Isn't it? Yeah. So some points here. Sea ice breaks approximately perpendicular to the wave direction. Okay, but there are some discrepancies towards the coast because you have the stress state that's changed. Freshly broken ice has an elongated shape, so with cracks oriented along the waves, but they do not survive for long. They still tend to be kind of isotropic in no time. And the breakup fronts move at roughly 10% of the group speed. Okay, and we have I have graphs, quantitative graphs later, but it's much slower than the propagation of the waves. So we have 3 events. This is another one, and I'm showing you that we are also able to extract the velocity field, and that we do that for a reason. Of course, we can study deformation, but what we want to do is to see how the flow size evolve during the wave event. But we want to see the evolution for the same ice. So we follow the same area of ice here. So that's a mask, and that mask is advected with the flow deformation field extracted from the PIV metal. So within that image, this is an example. So what we do is we do a segmentation algorithm and try to we have an artificial fragmentation scheme so that potato-shaped flow that looks like 2 flows in contact are broken up. So there is some uncertainty about that. We have many images, so we do some averaging over pairs of images to obtain the flow size distribution I will show you. So this is just for that event. We have typically 4 to 5 second waves here, and here this is at the AWAC. So we have roughly 1 to 1.5 meter waves here. That's going to be useful for assessing some numbers. So what we do here is plot the cumulative area fraction. So starting with the large flow, so the black point is the area, the total area of the unbroken sea ice, which is here, which would be it should have been here. It's total, and then from that point we sum. So here we still have unbroken plates. That's fairly large, and then contributes to a high fraction. Oops, sorry. And then we accumulate successively to the small flows. So what we see is that it reaches an equilibrium cumulative area fraction. So to the fact where flows are they don't break up anymore. It happens in, let's say, 1 hour and a half approximately. So that enough time for the waves to have propagated through that marginalized zone a long time. So it's not instantaneous process. So there's this idea to reach a probability of breakup. It's not that bad. And what about the scale? So this is the minor axis. So we get rid of the fact that we have elongated flow. We just check the minimal axis. That should be relevant to the scale of the wave. And so we can do many things. We can look at the wavelength in the open water. Here it's 32 meters. If you divide that by 2, then you fall approximately on the maximum flow size width whenever everything's done. So, and here, because the ice is broken up, then waves are propagating pretty much as if they were in open water. While right at the breakup, then it may be clever to use the wavelength in sea ice as a flexible wave propagating, and it's a little bit higher, and it corresponds to twice the minor axis we have for the longest freshly broken flows of the minor axis. And this would be a flexural scale, flexural length scale, which is smaller than all these numbers that we obtained. So we haven't reached the minimal size, let's say, that permitted by flexure. So here is the like the progression of the breakup front. So it's the position versus time. Here we do for one event, we do at many transects just to average things out. And here it's for our 3 events averaged out. So we see that there are 2 events which happen at the same speed. Unfortunately, one we have the waves, one we don't have the wave propagation, and the other one we don't have as well wave measurements. But you see that it's much smaller than either the group velocity in ice or the group velocity in open water or even the phase velocity. So that's something to remember. Okay, so having seen this, I'm going to go a little bit faster here because it's just the same thing I've presented, like the flow breakup parameterization. What we did during that stage, actually this week, we coded like a new one based on what we learned from these experiments. So it takes time for the flow to break up, first thing. And then the significant strain may be more that's actually breaking up the ice is probably more a bandpass significant strain, like the strain that is relevant to the flow size we will look at. So we changed that to a bandpass significant strain, and then we work out the probability and put that in the formalism of proposed by Horvath and Zhang. And we end up with that equation where we have a time scale here, which is proportional to the wave period, as a factor to delay the breakup. And here are some results. It's just, it doesn't intend to reproduce what we've been observing. But here's the mean ice thickness profile from 0 to 500 kilometer distance, and it's a mean ice profile because we specify an ice thickness distribution. Okay, that it's probably a Gaussian or something like this, just to give some variability in thickness as well, because we can work out the breakup as a function of thickness. We have the mean flow size that's produced. So mean flow size now, it's not the mean of a power law, it's the mean of our actual distribution that we have computed. And this is the significant wave height decreasing as wave attenuates. So here, after 5, I will show you the flow size and distribution, thickness distribution at different places in that transect up to 255 kilometers, just before it stopped breaking. So that's what it gives, and there's no minimum forced for the flow size. So it's just driven by the waves and the flexural failure of the ice of a given thickness. So we have ice thickness here from 0 to 6 meters and flow size for 0 to 200. Above 200, you don't have enough wave energy to break anything. So that's after 5 kilometers, 50 kilometers, 125 kilometers, and 225 kilometers. So I don't know if from that you hardly see a power law, you hardly see something that relates to observation done at the large scale, but we're looking at tiny, at a point, let's say. And what happens in the marginalized zone is you have to add up all these processes that melts ice, that move ice away. So eventually, if you take all these things and you put that in a model that is now more viscous and that move things around, then maybe you can start to explain what's going on with these observations at the large scale, of course. Can I take 4 minutes just to end up with talking about the wave radiative force, because we have been carried a lot of in situ field work as well. We've been on the ice, not just taking pictures of it. And here is like a sketch of an experiment we did, an outing. So this is the bay here. The ice edge is here. We have the shear line. So this is land fast, and this is all broken up brash with waves propagating. You can see the waves, Mike? So there are waves, and you'll see waves here. I'm going to play a small video, not too long, Veronique, I promise. Sorry. So that's going to show you as well another part of the work we do. Oh, sorry. Start that again. Okay. So we use an ice canoe to access the unstable ice. So we don't walk on the ice. And that may be a tool to use in river ice, but I'm not sure. But it's stable, and it's been used in Canada for 100 years to transport people from the land to islands or to cross at between Quebec and Lévis. And now it's used as a sport mostly. So there's a championship going on in the St. Lawrence estuary from Montreal to Rimouski. It's the eastern race. Here we are in the bay. We are in the so this is the end of the bay here, and so we carry we measure thickness. We deploy the aqueduct here, which is the we measure the turbulence over 1 meter thickness under the ice. So with the attempt to measure how wave energy could be dissipated in turbulence in the water. Those are high precision wave buoys with 6 degrees of freedom, pretty much like the one used by ONR here, but in mayonnaise pot. And now we are in the wave, in the marginalized zone. This is the inner bay. So the bay is there, the island is probably here, and now I look offshore, waves are coming towards us. And I suggest I mean, you can take time to look at this, because how the waves propagate in sea ice, for those of you who try to model that, that's pretty informative as what could be the viscosity or flexural, I don't know. Can you see pressure waves in that? I'm curious to try to detect that. But you have, it's all broken up, but you still have discontinuity in the movement. Here is the one wave buoy that was standing there, measuring the waves from the ice above.
It's very high thickness.
It's yeah. It's when we do the sorry.
The ice is thin as well, but I suppose it's scales.
This is it can be up to 80 centimeters, and the reason why is I'm going to explain. So you have the wave here. So we deployed 5 buoys. The outer one, that's the wave spectrum. We see that the frequency is decreasing, the peak frequency is decreasing as waves travel in. Of course, the energy is decreasing as well. It's centered on 4.5 seconds. So of course it's not 10-second waves peak, like John's spectrum. What we see though is this is the spreading, the directional spreading of. So when it's 1, it's not spread, and when it's below 1, it's more spreaded. Now the wave energy decays exponentially as a function of distance. We don't attempt to model that, but we just measure it. And with that in mind, if you take into account that all the wave momentum is absorbed by the ice, then it can translate to a force, which is also accumulated from the ice edge. And if you compare that to the wind, like because it's really short, it's 100 meters, then the wind stress acting at a particular point is really still low in that marginalized zone, but the wave stress is much higher here. And if you compensate that you balance it with a Mort-Coulomb compressive strength, then you can compute a equilibrium thickness for that given forcing. And combining all the measurements, we see that and adimensionalizing the thickness on the equilibrium thickness, we reach that profile here, exponential profile. There's a lot of scatter, but if you average them out, they fall on that line here. And that is my last slide. This is conveyed to a definition of the marginalized zone dynamics as a function of the wave force acting on the ice, which in our case was about 1 to 4 kilometers. So all the significant forcing that has been pushed on our marginalized zone came from the ice, from that argument here. So we try to, of course, continue that field work in order to answer these questions. But that's what the data has to tell. Thank you very much.
Thank you.
I just want to thank, there's a lot of people involved in this, so I just want to thank them.
Comments, questions, Dany?
Thank you, Dany, for a fantastic talk. Let me start by saying that it looks like, and I believe it is, wave-based breakup in Beidou-Haha. But I feel the need to be awkward, so I will be.
Yeah, we never succeed. Our goal is to be there, like have the wave buoys on the ice before a breakup, and then.
Let me explain my my devil's advocate thinking. In the central pack, well away from the ice edge,
Yeah.
in response to wind stresses, no waves. Okay, you have breakup into flows, just like you've shown in those photographs. Okay, very similar shape of the flows, etc. So, how do you know for 100% certain there's not wind breakup causing those breakup flows on the ice? Do you have wind measurement stresses?
We never observe that without waves. Like here we can see waves, and we also measure waves. Whenever there are waves measured, and we look at the
Well,
ice.
I would suggest that wind creates waves.
But
So-
Dany,
Okay, totally. But okay, I can show you other videos that are not there, but swell was propagating much less amplitude, of course, but there was still a 4-second or 3-second swell coming in, and yeah.
Like I say, I agree with it. It's
Yeah.
breakup, but the stuff you've shown
But-
today hasn't demonstrated it's not wind stress.
Yeah,
but you
and-
could easily show that.
Okay.
Okay. So,
And how can you show that? I mean,
well, let me explain.
Okay.
So models, there's a model has been developed by Mark Hopkins, Thorndike, myself. Okay, which tells you the size of the blocks that form in response to wind stress. Okay. If those blocks are simply much bigger than what you've observed, then it's not wind stress. Okay. So
are much bigger than, okay, so it prescribes
do
like,
a back the envelope calculation using the formulas that exist, and you'll be able to tell.
I think that's your job, Dany, not.
I can't hear
I
you.
think that's your job. I mean, from Shackleton onwards, every time there's any kind of waves, no one's been in the margin and this ice and observed waves and not seen it break up. It happens really quickly. As soon as the waves arrive, there's just countless examples of it.
And I agree with you.
I mean,
I agree with
maybe
you, but if you want to close the argument, okay, close the argument.
Well,
okay.
In your last slide, why was there that incredible scatter in the individual measurements?
I should show you
other-
the soup we're in. So the measurements are done with a stick. We are in a canoe, and then we plant a stick, and the ice is variable, and we haven't, took the time of taking 20 measurement into like a 10 meter across. And the way sea ice was in most of these experiments is like a soup of brush that's been compressed by the waves, which is approximately 80 centimeter thick. And then you sometimes, and that's relevant for rafting, but we saw a chunk of ice like a meter wide. They have been strongly eroded by friction because you have these sea ice on top. And then we dug up into it. And first it's hard to in fossilized and brush ice to know what's the thickness, with a stick. But and then by digging into that flow, we saw that there was another similar flow under, so clearly detached. Because they're small, we could push on it and detach them and see them both, that they were one on top of each other. 2 40-centimeter flow. So we use that like as also a way to try to measure the fossil ice. And of course, like trying to measure ice, it's measure ice thickness in that kind of condition. It's difficult. So we try to have I have the like the measurement scatter, and from that you can see where the inhomogeneity sums up into that average. But I think I put that on the ice, being inhomogeneous. What we try to do, of course, is knowingly, ice thickness is super important to quantify. So we have submitted a proposal to equip the ice canoe with a EM device. So that will get us transects of ice thickness, and then we can do proper averaging across and along.
Evgeny?
So continue Dany's argument, right? So continued argument which Dany presented, whether the breakup is caused by waves or not. Looking at your videos, you have a very strong tidal current here, which is probably in excess of 1 meter per second. So could it be that part of the fragmentation happened due to the currents? Not the initial breakup, but the actually fragmenting flows in the smaller pieces.
Yeah. Possibly. Possibly. We haven't measured it. But there were waves in all of the measurements, that the events that we've seen. Yeah, there's still to be proven. But okay, in these experiments, of the 3 events here, we measure the currents. Because what I showed, the breakup events are not those who are here, and when we measure the currents, currents are not, and we can compute the stress as well with the distance, and it was not significant compared to the wave forcing, for example. But I don't have that answer for all the events.
Let's take the last question, actually. Sorry about that, because time is running here.
Yeah.
Somewhere in the beginning you showed the rheology, so you had a term that implies compressibility.
Yeah.
So
compressibility, the compressive strength, yes. Yeah.
so the one that
Yeah.
is proportional to the bulk viscosity.
Yeah.
So I didn't understand what compressibility of what.
Oh, so this is how I was presenting the sea ice rheology as they are used today. They've been used for a long time. This ellipse viscoplastic rheology. So that this yield curve separates from solid or highly viscous behavior to plastic flowing. So this pressure here, isotropic compressive strength, is a parameter that decides whenever the ice will fails in compression. My argument is that looking at just the images, and if you break up flows around and you have a shear stress acting on it, then the yield curve in that dimension, so this is the shear strength, may be less. So, okay, and now this parameter is not compressive strength, it's shear stress, so pure shear. So if you have all broken up sea ice, it may shear.
Yeah, I mean, you have a pressure term up there.
Up there,
Then
yeah.
you have epsilon dot kk, right?
Yeah.
So that's the divergence of the velocity, and that's supposed to be.
Yeah.
So if ice is, I mean, okay, so that's supposed to be 0 as far as I understand.
It's really low within here, but it can be high whenever the external stress reaches that.
So d view is non-zero in your model.
Yeah.
I guess
And
we-
then you can add you can have thickness
Oh,
growing.
so that implies changes
Of
in
course,
thickness.
of
Oh,
course,
okay, so
of
now-
course.
now
Isn't
I
it?
guess we stop here because
Yeah. Thank you, Kai.
continue during the coffee break.
And Luke, we talk.
Thank you very much
Thank you.
anyway. Thank you. Now that we have a well-earned coffee break and